Large language models, or LLMs, have become essential tools in areas like code generation, literary creation, and news writing, boosting productivity significantly. However, their widespread use raises serious concerns about misinformation and intellectual property theft. To address these issues, watermarking has emerged as a key technique. Watermarks are embedded signals in the model's output that help identify machine-generated text and trace it back to its original source. In this paper, researchers from East China Normal University explore a phenomenon called watermark radioactivity. This occurs when watermarks from a teacher model, which is the original trained model, are unintentionally passed on to a student model through a process known as knowledge distillation. Knowledge distillation is a method where a smaller, more efficient student model learns from the outputs of a larger teacher model, mimicking its behavior without needing access to the teacher's internal details. On the positive side, watermark radioactivity allows us to detect unauthorized knowledge distillation by checking for these watermark traces in the student model. For instance, if someone tries to create a copycat model illicitly, we might spot the watermarks and prove the theft. Studies have shown that both logit-based and sampling-based watermarking methods can be detected this way, with sampling-based ones being especially useful in black box scenarios, where we only have access to the model's outputs, not its inner workings. However, this inheritance of watermarks also creates vulnerabilities. Adversaries could exploit it to launch attacks that weaken or manipulate these watermarks. Specifically, the paper focuses on two types of attacks: scrubbing and spoofing. Scrubbing attacks aim to remove or weaken the watermark, making it hard to detect the model's origin. Spoofing attacks, on the other hand, involve forging watermarks to falsely attribute content to a different model, potentially blaming a safe model for harmful outputs. Existing methods for defending against watermark attacks mostly target scrubbing, like protecting the teacher model from removal attempts. A few address spoofing, but they don't handle both simultaneously and often require access to the model's internals, which isn't always possible in real-world black box systems like Claude or GPT models. To fill this gap, the researchers propose a new framework called Contrastive Decoding Guided Knowledge Distillation, or CDGKD. This unified approach enables bidirectional attacks under unauthorized knowledge distillation. Here's how it works. First, they use contrastive decoding to generate corrupted or amplified watermark texts. This involves comparing the outputs from the student model with those from a weakly watermarked reference model. By analyzing the differences, they can identify and manipulate the watermark signals. Then, they apply bidirectional distillation. For scrubbing attacks, they train a new student model that learns to produce outputs without the watermarks, effectively removing them while keeping the model's overall performance intact. For spoofing attacks, they train the student model to incorporate fake watermarks, making it seem like the content comes from a different source. The researchers conducted extensive experiments to test CDGKD. They found that this method successfully performs both types of attacks without significantly degrading the student model's general capabilities, such as its accuracy in generating coherent text. For example, in tests with various LLMs, the framework maintained high utility in tasks like text completion while altering or eliminating watermarks. These results highlight a critical weakness in current watermarking schemes. Watermarks aren't as robust or unforgeable as we might hope, especially in scenarios involving knowledge distillation. This underscores the need for developing more advanced watermarking techniques that can withstand these attacks. In the introduction, the paper delves deeper into the background. It explains that generative watermarking, which modifies the model's output during generation, is preferred over post-hoc methods because it doesn't require extra processing. Most modern techniques work at the token level, partitioning vocabulary into green and red lists to bias the model's choices or altering the sampling process. The paper also notes that while watermarking helps combat misinformation by flagging AI-generated content, it must evolve to handle adversarial threats. For instance, in black box settings, where attackers can't directly access model weights, indirect methods like those in CDGKD become particularly dangerous. Building on prior work, such as Gu et al.'s findings on watermark detectability, the authors emphasize that sampling-based distillation is attractive for its flexibility. But they warn that without proper safeguards, these systems could be exploited to indirectly weaken teacher model watermarks. Overall, the experiments demonstrate that CDGKD is effective and efficient. It preserves the distilled model's performance, meaning the student model remains useful for practical applications even after the attacks. This efficiency is crucial because attackers often prioritize maintaining functionality while evading detection. The paper concludes by stressing the broader implications. As LLMs continue to grow in influence, with systems like Claude and GPT being deployed in black box formats for security, we must prioritize research into robust and unforgeable watermarking. This includes exploring new defenses against both scrubbing and spoofing in distillation contexts to protect intellectual property and ensure the integrity of AI-generated content. In summary of the findings, the author's work reveals that while Watermark Radioactivity offers detection benefits, it also opens doors to sophisticated attacks. Their CDGKD framework serves as a proof of concept for unified attacks, urging the AI community to innovate and strengthen watermarking technologies. This research is a wake-up call for developing more resilient methods to safeguard large language models against evolving threats.